Hey everyone, and welcome to another deep dive. Today we're going to be diving into a really fascinating paper called Orchid, Image Latent Diffusion for Joint Appearance and Geometry Generation.
Yeah, it's a pretty amazing paper.
It is, and it's got quite a few authors too.
It does, yeah.
We've got Zijian, Xingyu Zhao, Jiagu, Chen Sun, Heng Zhao, and Zhuxian Lin.
Quite the lineup.
So what we're going to be talking about in this deep dive is how this model can generate a 3D scene, including a color image, from a single text prompt.
Yeah, that's one of the really amazing things about it.
Yeah, it really is.
So to start off, maybe I can give a little bit of an overview about what this paper is really all about.
Yeah, that'd be great.
So the core idea behind Orchid is that it leverages a new type of diffusion model that can jointly encode both appearance and geometry information.
Okay, that sounds really cool.
Yeah.
So in the past, researchers have tackled this problem of 3D scene generation by treating appearance and geometry as separate things.
Yeah, exactly.
So you'd have one model trying to generate the textures of a flower or something, and then another one trying to figure out its 3D shape.
Exactly, and that could lead to some inconsistencies.
Yeah, it sounds like it would. But Orchid tackles this problem, like you were saying, by handling both appearance and geometry together.
Right.
And that leads to some really impressive results from what I've seen.
Definitely.
Okay, so let's jump into an example because I think that will help me understand this better. I was looking at this paper, and one of the examples they give is generating a 3D scene from the text, a Japanese lily.
Ooh, that's a good one.
I thought so. So how does Orchid actually achieve this?
Okay, so Orchid has these two main components.
Okay.
A joint latent space variational autoencoder, VAE, and a joint diffusion prior.
Okay. Let's break those down one by one.
Sure.
What's this joint latent space VAE all about?
So the VAE, it's like the encoder part of the system. What it does is it takes the color, depth, and surface normal information of a scene and compresses it into a smaller code.
Okay, so it's basically compressing all of that complex 3D information into something more manageable.
Exactly. And it does this by learning to represent the appearance and geometry in this kind of joint latent space.
Okay, so it's like a blueprint that captures both the look and the feel of the scene all in one place.
Yeah, that's a good way to think about it.
Okay, I'm following so far. But now we have this compressed code. How do we actually go from that back to a full-fledged 3D scene?
Right, so that's where the joint diffusion prior comes in.
Okay.
This is the decoder part of the system. It takes that compressed code from the VAE and uses it to generate all three things: the color image, the depth map, and the surface normals.
So it's like it's decompressing the information and rebuilding the entire 3D scene.
Precisely. And the key to making all of this work is that this diffusion model is trained on a massive data set.
Makes sense. Got to have lots of data to train these things.
Right. And the data includes color images, depth maps, and surface normals. And this is where it gets really interesting. The data is both real and what they call pseudo-data. Wait, pseudo-data?
Yeah. What they did is they took a bunch of images, and then they used existing pre-trained models to predict the depth and normal information for those images.
Oh, that's pretty clever.
Yeah.
So they basically generated extra training data by leveraging these pre-trained models. But I'm curious why they even bother using the pseudo-data. Why not just stick to the real stuff?
So the real-world data, while it's really important,
Yeah.
it can be really time-consuming and expensive to actually gather, right?
Yeah, that makes sense.
You'd have to, go out there with special cameras and sensors and capture all that 3D information.
Yeah, it's not easy. So by using this pseudo-data, they basically created a shortcut.
Yeah, exactly. And it allowed them to get a much larger and more diverse data set, which is really important for training a powerful model.
Okay, so they've got this huge data set with both real and pseudo-data. They've got their VAE to compress the information and their diffusion model to decompress it and generate the 3D scene. It's all starting to come together now.
Yeah, it's quite a system. So the VAE is using this data. What's it actually doing with it? How does it learn to encode this joint information?
So the VAE basically works by learning to minimize the difference between the input, which is that color, depth, and normal information, and the output, which is the reconstructed version of that information after it's been compressed and then decompressed.
Okay, so it's kind of like a game of telephone, where it's trying to whisper the information through this compressed code and make sure the message comes out as clear as possible on the other side.
Yeah, that's a good analogy.
It's all about preserving the information as accurately as possible, even when it's been squeezed through this bottleneck.
Okay, so the VAE learns to do this really well because it's seen so much data.
Right.
But what about the diffusion model? How does it learn to generate a coherent 3D scene from that compressed code?
So the diffusion model works in a kind of interesting way. It starts by, during the training, it adds noise to the training data.
Okay.
So it takes those images and it gradually corrupts them with noise until they become almost unrecognizable. Okay, so it's kind of like making a mess of the data on purpose.
Right. And then the model learns to reverse that process. So it learns to take that noisy data and gradually remove the noise until it gets back to the original clean image.
So it's learning to clean up its own messes.
Exactly. And the more messes it cleans up, the better it gets at recognizing those patterns and being able to denoise images even when it's never seen them before.
So by learning to denoise, it's essentially learning to generate.
Exactly.
I'm starting to get it. It's like learning to draw by first learning to erase. Okay, so that's how the diffusion model learns to generate images in general. But what makes this diffusion prior so special?
So in the case of Orchid, the diffusion process isn't applied to the images directly. It's applied to that joint latent space that the VAE created.
Right, that compressed code that captures both the appearance and the geometry. So it's not just generating the color image, it's generating the entire 3D scene all at once.
Exactly.
And that's what allows Orchid to create these really coherent and consistent 3D scenes.
Right, because it's learned to represent all of that information together in a way that makes sense.
This is really fascinating stuff. So we've got this VAE that compresses the 3D information and this diffusion model that learns to generate from that compressed code.
Yeah.
But how well does it actually work?
Well, the results are pretty remarkable, actually. In the paper, they show lots of examples where Orchid generates these incredibly realistic images of flowers, trees, rooms, you name it, all from just text prompts.
Wow, that's amazing. So I give it a text prompt like a majestic oak tree overlooking a serene lake, and boom, it creates a 3D scene that looks like a photograph.
Pretty much.
I'm just imagining all the possibilities with this technology, from gaming and virtual reality to architecture and design. It could revolutionize so many industries.
Absolutely. It's a really exciting development in the field of 3D content creation.
But before we get too carried away, let's take a step back and look at the historical context. What kind of research led up to this breakthrough? What were some of the challenges that researchers had to overcome to get to this point?
So, the history of 3D scene generation is a long and winding one, but I think we can break it down into a few key stages. In the very early days, people were mostly focused on creating 3D models by hand, using specialized software and a lot of manual labor.
Right, it was a very time-consuming and tedious process.
Yeah, exactly. And the results were often quite limited in terms of realism and complexity. Then, with the rise of computer graphics and 3D modeling software, things started to get a bit easier. But it was still a very specialized skill, requiring a lot of technical expertise.
And the models themselves were still pretty basic, right?
Yeah, they were mostly composed of simple geometric shapes and textures. They didn't have that organic, realistic feel that we see in the real world. Then came the era of deep learning, and that really changed the game.
Yeah, deep learning has revolutionized so many fields, and 3D scene generation is no exception.
Exactly. With deep learning, we could suddenly train models on massive data sets of 3D objects and environments, allowing them to learn the intricate patterns and relationships that govern the structure and appearance of the 3D world.
So instead of manually programming the rules, we could let the models learn from the data itself.
Precisely. And that led to some really exciting results. Early deep learning models were able to generate some pretty impressive 3D scenes, but they still struggled with realism and consistency, especially when it came to capturing the interplay between appearance and geometry.
Right, I remember seeing some of those early results, and they were definitely cool, but they often had that uncanny valley feeling where they were almost realistic, but not quite.
Yeah, exactly. And that's because, as we discussed earlier, most of those models were treating appearance and geometry as separate tasks. You might have one model trying to generate the color and texture of a tree bark, while another model was trying to figure out the shape and branching structure of the tree, and that often led to mismatches and inconsistencies, making the scene look artificial.
Like trying to build a house with two separate blueprints, one for the exterior and one for the interior.
Exactly. And that's where Orchid comes in. It takes a more holistic approach, learning to represent both appearance and geometry within a single unified framework. And that's what allows it to achieve that level of realism and consistency that we see in its results.
It's like finally having a single blueprint that guides the construction of the entire house, ensuring that everything fits together seamlessly.
That's a great analogy.
Okay, so Orchid is clearly a major step forward in the evolution of 3D scene generation. But what are some of the next challenges on the horizon? What are the frontiers of this field that researchers are still grappling with?
That's a great question. I think one of the big challenges is going beyond static scenes and creating dynamic, interactive 3D worlds.
Yeah, that would be amazing. Imagine being able to step into those virtual worlds and interact with them in real time.
Right. But that would require a whole new level of complexity. We'd need to teach these models to understand physics, to simulate motion and collisions, and to respond to user input in a natural and intuitive way.
And let's not forget about the ethical implications of creating these hyper-realistic virtual worlds.
Absolutely. We need to think carefully about the potential impact on society, on our relationships, and on our sense of reality.
These are big questions, and I don't think there are easy answers, but they're questions we need to start grappling with now as this technology continues to evolve.
I agree.
Well, I think this is a great place to take a break and shift gears to our Novel Notions segment, where we'll explore some even wilder research ideas inspired by Orchid.
Sounds good.
I can't wait to hear what you've come up with. We'll be right back after a short break.
See you soon.
Welcome back, everyone. So before the break, we were talking about all the different pieces of Orchid.
Yeah, it's quite a system they've put together.
Yeah, it really is.
It's fascinating how it all comes together to generate these incredibly realistic 3D scenes from just a simple text prompt.
Right, it's like magic.
Okay, so we talked about how the VAE compresses the 3D information into this joint latent space.
And then the diffusion model takes that compressed code and uses it to generate the entire 3D scene.
Exactly.
But I have to admit, I'm still a little fuzzy on how this diffusion model actually works. It's like it starts with noise and then somehow magically transforms that noise into a coherent 3D scene.
Yeah, it can seem a bit counterintuitive at first,
It does.
but it's actually a really clever process. So during the training phase, the model is fed a bunch of training data, like those color images, depth maps, and surface normals.
Right.
But instead of just learning from the clean data directly, the model first adds noise to the data.
Okay, so it's intentionally corrupting the data.
Yeah, exactly. So it gradually adds more and more noise to these images until they basically become like these blurry, unrecognizable blobs.
It sounds kind of destructive, doesn't it?
It does, but it has a purpose.
Yeah.
So then the model is trained to reverse this process.
Okay.
It has to learn how to take that noisy data and gradually remove the noise until it recovers the original clean image.
So it's like learning to clean up a really messy room. The better it gets at cleaning up the mess, the better it gets at recognizing what the clean room should look like.
Exactly. And by learning to denoise, the model is essentially learning the underlying structure of the data, like the relationships between the different pixels and the different features.
That makes sense. So by learning to undo the noise, it learns how to create images from scratch.
Exactly. And once the model has been trained to denoise, you can give it a starting point of pure noise, and it will be able to gradually refine that noise until it generates something that looks like a real image.
Wow, that's pretty amazing.
Yeah, it is.
So it's kind of like the model is learning to be an artist, but instead of starting with a blank canvas, it starts with a canvas full of random scribbles, and then it has to figure out how to turn those scribbles into a masterpiece.
Yeah, that's a great analogy.
Okay, so that's how diffusion models work in general. I think I'm getting it now. But what makes this diffusion prior in Orchid so special?
Right. So in the case of Orchid, the diffusion process isn't applied to the images directly. Remember, we have that latent space.
Yeah, that joint latent space that the VAE creates. So are you saying that the diffusion model is operating on that compressed code instead of the raw images?
Exactly. So it's not just generating a color image, it's generating all three things, the color image, the depth map, and the surface normals all at once from that compressed representation.
Oh, wow. I see. So that's how Orchid maintains consistency across all three modalities. It's all being generated from the same underlying information.
Exactly. And that's what allows it to create these incredibly coherent and realistic 3D scenes.
Okay, that makes a lot of sense. So we've got this VAE that compresses the information and this diffusion model that learns to generate from that compressed code, and it all comes together to create these incredible 3D scenes from just a text prompt.
Yeah.
It's mind-blowing.
It is. It's a really powerful example of how deep learning can be used to tackle really complex problems like 3D scene generation.
Okay, so I think I have a good grasp of how Orchid works now, but my mind is already racing with possibilities. What if we could push this technology even further?
Oh, yeah.
What if we could create 3D scenes that aren't just static images, but dynamic, interactive worlds that we could actually step into and explore?
Yeah, that would be incredible. I mean, imagine being able to walk around in a 3D environment that was generated entirely from a text description, or maybe even from your own imagination.
It would be like stepping into a dream.
Yeah, exactly. But to get there, we would need to overcome some pretty significant challenges.
Like what?
Well, for one thing, we'd need to teach these models to understand physics. Right now, Orchid is really good at generating static scenes. But if we want to create dynamic worlds, the models need to be able to simulate things like gravity, motion, collisions, all of those things that make the physical world behave the way it does.
That makes sense. It's
Yeah.
one thing to create a realistic looking tree, but it's another thing entirely to make that tree sway in the wind or fall over if you push on it.
Right. And then there's the challenge of interactivity.
Yeah, how do you make these virtual worlds responsive to the user?
Exactly. We'd need to develop new ways to connect these models to external input, like sensors that capture your movements, or even brain-computer interfaces that can read your thoughts.
Wow, that's getting really futuristic.
It is. But it's not entirely out of reach. There are already researchers working on these kinds of technologies.
It's exciting to think about the possibilities, but as you said, there are also ethical considerations to keep in mind.
Oh, absolutely. I mean, if we're talking about creating these hyper-realistic virtual worlds that people can lose themselves in, we need to think carefully about the potential consequences.
Yeah, like what happens if people start to prefer the virtual world to the real world? What happens to our relationships, our sense of community, our sense of self?
These are big questions, and I don't think we have all the answers yet. But it's something we need to start thinking about now, before this technology gets too far ahead of us.
I agree. It's important to have these conversations and to approach these advancements with both excitement and caution. Well, on that note, I think it's time to take another quick break, and then we'll come back with our Novel Notions segment, where we'll brainstorm some even wilder ideas inspired by Orchid. Stay tuned. Welcome back to the show. So before the break, we were really diving into some of the potential implications of creating these hyper-realistic, interactive virtual worlds.
It's really mind-blowing to think about, isn't it?
It is. It is. But, like with any powerful technology, we have to think about the potential downsides too, right?
Absolutely.
We can't just get swept away by the excitement of all the cool things we could do without also considering, the potential risks and ethical concerns.
Yeah, you're absolutely right. There are definitely some ethical considerations we need to be thinking about as these technologies develop.
Like, what are some of the things that come to mind for you when you think about the potential downsides?
Well, I think one of the biggest concerns is, the potential for addiction and escapism.
Yeah.
I mean, if these virtual worlds become so realistic and so engaging, it's possible that people might start to prefer them to the real world.
Right.
And that could have all sorts of negative consequences for individuals and for society as a whole.
Yeah, it's like what happens to our relationships, our sense of community, our connection to the physical world if we're all spending all of our time in these virtual spaces.
Yeah, those are really important questions to consider. And it's not just about addiction either.
Yeah, what else?
There's also the potential for these technologies to be used for malicious purposes.
Right. Like creating even more convincing deepfakes or spreading misinformation or propaganda.
Exactly. So it's really important that we develop these technologies responsibly and that we think carefully about the ethical implications from the very beginning.
Absolutely. I completely agree with you. But for now, let's maybe shift gears a little bit and get back to our Novel Notions segment. We talked about a lot of cool possibilities with Orchid, but I'm always curious to hear, what other wild research ideas this kind of technology sparks in your mind?
Oh, there are so many. But one that I've been thinking about a lot lately is, what if we could use Orchid to bridge the gap between the virtual and the physical world?
Okay, have you need?
So imagine you have a real world object, like a sculpture or a piece of furniture.
Okay.
What if we could use Orchid to generate a 3D model of that object simply by taking a picture of it with our phone?
Oh, that would be amazing. It would be like having a magic wand that could instantly transform the real world into a virtual one.
Yeah, exactly. And think about the applications.
Yeah. What can we do with that?
Architects could create virtual replicas of buildings just by scanning them with their phones.
Oh, that's a cool idea.
Designers could capture the shape and texture of real-world objects and seamlessly integrate them into their virtual
Wow,
creations.
that'd be so cool.
And doctors could use 3D models generated from medical scans to plan surgeries or create personalized prosthetics.
Wow, the possibilities are really endless, aren't they?
They really are. It would completely revolutionize the way we design, build, and interact with the world around us.
I'm sold. But how would we actually make this happen? What kind of research would need to be done?
So the key would be to train Orchid on a massive data set of paired images and 3D models.
Okay.
So it could learn to associate the visual features in an image with the corresponding 3D geometry.
So instead of starting with a text prompt, we'd be feeding Orchid real-world images and asking it to create a 3D model based on what it sees.
Exactly. It's definitely a challenging problem,
Yeah.
but I think it's one that we could solve with enough data and the right algorithms.
Okay, I love it. It's a super ambitious idea, but that's what makes it so exciting.
It is.
Well, I think this is a great place to wrap up our deep dive into Orchid. We've covered a lot of ground today,
Yeah, we have.
from the technical details of how the model works to the potential implications for various industries and even the ethical considerations we need to keep in mind.
It's been a great discussion.
It really has. So for our listeners out there, if you're interested in learning more about Orchid and other fascinating developments in the world of AI, be sure to check out the show notes for links to the paper and other resources. And as always, thank you so much for joining us on this deep dive. Until next time.
See you then.